Okay, hi. My name is Pim Moeskops from the Medical Image Analysis Group of Eindhoven University in the Netherlands. I will show some examples of how we applied deep learning to brain MRI segmentation. So what we saw, for example, in Andrew's talk are these kind of networks. So we have an image of a cat or a dog as input, and then we have this network, and in the outputs we have, do we see a cat or a dog or a chihuahua or a muffin? Or so, I mean, that's interesting, but if we want to do segmentation in brain images, for example, then we'd like to see a decision for every pixel or voxel in the image. So if we have a brain image like this, so this is, I've mostly worked on neonatal brain imaging, and so this is a brain of a preterm infant born before 28 weeks and then imaged at 30 weeks of age. It's a coronal T2 weighted image. So in segmentation, what we'd like to do is label every voxel in the image as belonging to, for example, tissue types in this case. So what we see here, so at this age, most of the white matter is still unmyelinated. And then we have different classes for the cortex, for the CSF outside of the brain, the ventricles, the basal ganglia, brainstem, cerebellum. And then we have, you can see here, just the small pink dots are the start of the myelinated white matter. So the most straightforward approach of translating these convolutional neural networks to segmentation networks is going for a patch-based approach. So what you actually do is you take a patch of the image and you and the output of your network will then be, does this the image of the pixel in the center of the patch, does it belong to white matter or gray matter? And so you can go over the whole image like that, and in this way come to a full segmentation of all of your whole image. So this could be a patch like that. So this is a 25 by 25 voxel patch from one of these images. So you could see some structure in here, but it's still difficult to see what it actually is. Where are we? If I take another one, this looks kind of similar. You can see this dark band appearing, a bit gray on the right side, and a bit higher intensity on the left side. But if we zoom out from this, so the 25 by 25 pixel is now indicated by the box, and this is now 51 by 51 voxels. You can see that we're actually in quite a different location in the brain. And if we zoom out a bit more, you can see that the left one was located at the cerebellum, and the right one was located at the cortex. So they were even located in the same image slice. So what this shows is that to make a decision about every pixel, we need a large enough patch or receptive field for our network to be able to make this decision. Similar to how you would do it yourself, you need a bit of context to be able to see where you are in the brain. So this idea we can take to convolutional neural networks. So you see here the patches of these three sizes that I showed before, 25 by 25, 51 by 51, and then 75 by 75. Then you can see these convolutional neural networks based on convolution layers, max pooling layers, just as we saw in this tutorial. And then, so we have branches of this network for each of the patch sizes, and in the end, they are combined to make a decision about to which tissue class does the voxel that we are currently belong to. So we can train this network, and see if it performs well. So it consists of convolution operations, but what is it now exactly learning? And these are the kernels that were trained. So these are just in the first layer. So what we can do is see what happens what happens if we apply a kernel. Just take one of the kernels, apply it to the image, and see what happens. So, for example, this. So you can see here that specific structures in the brain are enhanced or suppressed. For example, here you can see that especially the outer border of the brain is enhanced, and the contrast between white matter and gray matter is decreased, for example. You can take another one. You can see here that this looks more like a horizontal gradient. And here this seems to invert the intensity. So you can see now that the gray matter is bright and the white matter is actually dark compared to the original T2-weighted image over there. So let's look at some results of this approach. So we have the image at the top, the reference segmentation in the middle, and then the automatic segmentation at the bottom. So it might be a bit small, but you can see that it looks quite, it seems to perform quite well. So these were the 30-week images, and this is now an image of these infants at 40 weeks. And you can see that the brain developed a lot, and you can see here that the pink structure, so the unmyelinated white matter, is especially difficult. So you can see that the network kind of grasps the location of the unmyelinated white matter, but the specific shape is difficult. But you can also see in the image that it's just very difficult to see in these images at all. Same things you can see. These are also images at 40 weeks of age, but just in the axial direction in this case. These are actually images of elderly patients of about 70 years old, and so we can show that we can use the exact same method to also not only segment these infants, but also segment adult brains or elderly brains. And this is then another one of an adult brain, but then in coronal plane. So to see how well these networks perform, we use dice coefficients, which shows the overlap between the manual and the automatic segmentation. So a perfect overlap would mean 1, and 0 would be no overlap at all. So we can see that for each of the 5 sets that the method performs quite well. And we can see this, so we can see for each tissue type that it performs well, and then we can see for the last one that the myelinated white matter is the difficult one. So I now showed segmentation of tissue types, but we can even take this a step further and do more the partitionation of the cortex and all the nuclei separately. So in this data set, we have 134 segmentation classes. You can see here a reference segmentation, and we can then show that our method can also do this quite well and achieves quite a high dice coefficient for this task as well. Here we show that we can also not only do tissue segmentation, but also incorporate segmentation of white matter hyperintensities in the same network. So usually the approach would be segment the white matter and look in the white matter for hyperintensities. What we now show here that we can just include it in the segmentation and based on these 3 inputs images, we can do tissue segmentation as well as segmentation of these lesions in one shot. And then here I show that the volume of white matter of the white matter hyperintensities corresponds well with the manual reference volume. And here I show that it detects most of the white matter hyperintensities recognized by in the reference standard as well. Okay, so this was this is one way of including or of applying deep learning methods to image segmentation and includes this multi-scale information. But of course, there are many more approaches. So one is what is commonly referred to as fully convolutional CNNs. So what happens here is that after this, the contracting path, there is an upsampling such that the output is the same size as your input. So you have an image as input and a full segmentation as output, or part of the or a patch as input and a segmentation patch as output. And then the multi-scale information is included by making connections from different locations in the network structure. And they are then combined to make one decision about the segmentation. The very commonly used UNet architecture takes this a step further. But instead of just upsampling the maps, there are also weights in the upsampling direction. So you have convolutions. You have just normal convolutions, and in the upsampling part, you also have deconvolutions or transposed convolutions. And then the arrows going from left to right make sure that there's also multi-scale information incorporated. So information that was extracted before can also be used further on the network. So these networks are image in, full segmentation out. We can actually do the same when we train the methods for in a patch-based method. If we would just have a simple network consisting only of a few convolution layers, we can. So this is a network with 3 layers that then has a receptive field of 7 in this case. We can just say we copy everything, and now we have an output of 5 instead of 1, and the receptive field still remains 7 from the original image. So every pixel in your output has a receptive field in the input image. And the same idea is used in dilated convolutional neural networks. So if you would have an input like this, if we apply a convolution operation of 3 weights or 3 elements, without dilation, this would mean we have a receptive field of 5 after just 2 layers. If we now start, so now the idea of this dilation is that instead of having the kernels next to each other, we actually skip elements. So dilation factor of 2 means we skip 1 element, and this results in a quickly increasing receptive field. So now with a limited number of weights and just 3 layers, we already have a receptive field of 9. And we can take this further. So if we would now add another layer with a dilation factor of 4, so we skip 3 elements, and this would already result in a receptive field of 17 after just 4 layers and without doing any max pooling at all. So the full network that the authors propose in this paper consists of first a few normal convolutions and then an increasing dilation factor, so that in the end the output has a receptive field of 67 by 67 in the original image. So this ID we used for a challenge on segmentation of a 6-month infant brain MRI held at MICAI last year. So these are the images that we're looking at, and the 6 months, the age of 6 months is especially difficult because the contrast between white matter and gray matter is kind of similar at this point, because after the 6 months, the contrast is flipping. So we took this ID of this dilated network and we applied it using the axial, coronal, and sagittal plane as inputs, and then made a decision about every voxel based on these 3 network branches. In addition, we also included a 3D input, so just a full 3D CNN. The input sizes are this 67 by 67, as we had before, and then the 3D input is a smaller box around the output voxel. So we compared a few settings here. These show dice coefficients for white matter, gray matter, and CSF. And if we shared the weights between the 3 branches in a network, and these were the results. And if we decoupled the weights, the results appear to be slightly better. And if we included this 3D network, it improved even further. So this is how that looks in the image. So we have a T1 and a T2 weighted images input. We then have the automatic segmentation and the reference segmentation there. So you can see that it corresponds quite well to each other. Okay, so Chris nicely introduced generative adversarial networks in the previous talk, so I can be quite short. So the idea is you have a generator network that generates data from a random input, and then we have a discriminator network that distinguishes generated from real data. We can take this ID also to segmentation. So this is an ID. So this is an image from the paper showing generating images of faces. Okay, so we can take this ID to segmentation. So instead of having a generator a network, we now have a segmentation network that produces a segmentation from an image as input. And we then have a discriminator network that distinguishes real manual reference segmentations from generated segmentations. And by motivating the network to be difficult to be such that it's difficult to distinguish segmentations, generated segmentations from manual segmentations, we believe it can improve our segmentation method. So this is a reference segmentation of an adult patient. And so here is if we train a network to without this adversarial approach, and we can see that it makes some quite severe errors. You can see at the arrows that here the part of the cerebellum is missing. You can see some holes in the close to the ventricles, and you can then see that these problems are reduced when we use this adversarial training approach. Here we have again the elderly patients, and you can see this same. You can see weird clusters appearing at unrealistic locations, and then this approach of making the segmentations difficult to distinguish from reference segmentation helps us in improving these kind of errors. So that was a visual look at these results, but you can of course also look at dice coefficients again. So this shows the dice coefficients for each of the tissue types, and then in blue you see the method without adversarial training approach, and then in green you see the results with this adversarial approach. You can see that it's for these specific images and with this network, it's quite drastically improved. For other images, the improvement is less in terms of dice coefficient, but still very consistently, it not only improves the visual performance, but also the dice coefficients. This is then with the dilated network. You can see that the results are already a bit higher as a baseline, but you can also see that it consistently improves the results. Okay, so segmentation is, of course, just one of the steps usually in brain imaging. In case of neonatal brain imaging, a pipeline could look something like this. So we have an image as input. We do a segmentation. And based on the segmentation, we'd like to compute some numbers that can tell us something about how well the infant is developing. So we could look at volumes, or we could look, for example, at the curvature of the brain, so we can see how well the cortical folding is developing. And based on such quantitative measures, we'd like to see if we can improve predictions. So, for example, can we predict their neurodevelopmental outcomes? So it could be IQ, it could be motoric tests, or any other neurodevelopmental outcome. So what we now also show is that we can actually skip a step in this process. So instead of going from an image to a segmentation, we can directly from the image predict the volume already. So without doing any segmentation, we can say, hey, this patient has this amount of gray matter volume. And you could say, and then this shows that these reference, so you can see on the x-axis the reference volumes, and on the y-axis the predicted volumes. You can see that they correspond quite well. So you could say, if you already have a segmentation method, why would you even try to directly predict volumes? But what this shows is that we can directly from the image extract relevant information without having to specifically focus on segmenting things first. So could this even mean that we could go skip another step and go directly to predictions from the images? So, of course, this is just a structural MRI scan. It's not the only thing that's acquired. So we could also, for example, there's an EEG that's normally acquired of these infants. So we could use a 1D convolutional neural network for this as well. And we could use our standard information, such as age and weight, and the education of the parents, for example. And all of these things can contribute to the performance of these predictions. And of course, we already know several things from the image based on these segmentations, such as the volumes, surface area, cortical thickness, measurements of cortical folding. So we can also just include those numbers in such a network as well. Such approach is especially nice if we can look into visualization of what the network is now learning. So based on what does the network make a decision. So if we can say that an abnormality in this specific region relates to the outcome, that can help us could even potentially help us in identifying new biomarkers from the images. But more on visualization will be in the next talk. So that concludes my talk. Thank you.
Thanks a lot, Pim.